Welcome, everyone. I'm David Bader, and I direct New Jersey Institute of Technology's Institute for Data Science. Welcome to our Wednesday Data Science seminar. And today we're pleased to have Michael Mahoney as our speaker. Michael is at the University of California at Berkeley in the Department of Statistics, and he's also at the International Computer Science Institute. He serves as the director of the NSF Tripods-funded Berkeley Institute on the Foundations of Data Analysis. And he's also on the National Advisory Committee of the Statistical and Applied Mathematical Sciences Institute. And he was on the National Research Council's Committee on the Analysis of Massive Data. Michael also runs the biennial MMDS workshops on algorithms for modern massive data sets. His research focuses on algorithmic and statistical aspects of modern large-scale data analysis. Much of his recent research has been on large-scale machine learning, including randomized matrix algorithms and randomized numerical linear algebra, geometric network analysis tools for structure extraction in large informatics graphs, scalable implicit regularization methods, and applications in genetics, astronomy, medical imaging, social network analysis, and internet data analysis. If you have questions during the seminar, please put them into the chat. We'll try to get to those near the end of the lecture. So thank you, Michael, very much for agreeing to talk.
So great. Thanks a lot, David, for the invitation. It's always good to tell people about some recent work that you've been doing that you're particularly excited about. And I'm glad to have the opportunity to talk about it here. As I was saying when we were chit-chatting before, the only thing better than being able to do this in person would be if I had been able to be there, or online would be as if I was able to be there in person. So, so in the absence of that, it's great to have the chance to tell you about some of the stuff that we've been working on recently. And what I want to tell you about, I guess, is some work on dynamical systems. And that's not had a particularly prominent role in a lot of the work in machine learning and AI and data science recently. And how maybe we can combine that with techniques from machine learning and AI and data science. And there's a range of ways to do this. And I think you can take, a machine learning approach and graft on some dynamical systems ideas, or you can take dynamical systems essentially and graft on a few set of machine learning techniques to make it seem a little bit shinier maybe. So what we want to do, I think, is try and combine in a reasonably principled way the two approaches. I mean, on the one hand, let's call it data-driven models, by which I mean loosely machine learning sort of models that are largely driven by the data and for which you're relatively ignorant about domain knowledge typically. And let's call it domain-driven models, which arise in science and engineering and economics and a range of other areas, where you really have strong domain-specific constraints or domain-specific understanding that in a lot of cases might really be at cross purposes with sort of state-of-the-art machine learning methods. So that's what we want to do. And I think it's a particularly challenging problem because the structure of machine learning theory really is very static. You take a data set, you cut it in half, you train, you test, you generalize. There's no time there. And time, most of us live in time, and most of us are interested in predicting tomorrow's data. You make this assumption that tomorrow's data will be similar to today's data. In some cases that's true, in some cases that's not. It's hard to validate that, whether that's the case or not, without asking counterfactual questions, which oftentimes might not be asked. So you can imagine a situation where I don't have any physics or engineering under the hood. I just want to make predictions about tomorrow's data, and I want to do it in a better way. You can also imagine a situation where I do have some knowledge of some domain. I know that I want to model fluid mechanics or climate science or something where I have some idea of the dynamics, and I want to capture that in some way. So we're going to actually look at both, and they have some complementary challenges, but I want to sort of talk about both. So some general thoughts, introduction and overview, and then I want to talk about two particular things. One of which is adopting one of the approaches that I said, basically you start from one perspective and graft some ideas onto it. So we're going to have physics-informed autoencoders, and essentially we're going to have a model and we tack on a regularization that is motivated by the dynamical systems, by a stability principle. And we actually have better results on this, but I like this example because it highlights, I think, if you adopt sort of the regular MO, even then you can pull out some interesting insight. In particular, we're going to find a regularization function that's just nothing that you would have come up with had you viewed things statically. Had you, it's not an L1 or an L2 or an L3, or it's nothing that you would have come up just from a machine learning textbook. It really uses the dynamics. And so we got some nice results there. They can be improved upon, as I said, but it highlights, I think, a disconnect that at least informed our understanding. And then I want to talk about something more recent, and I'm going to call this a continuous in-depth neural network. So neural networks are discrete things. They're models. They have 10 layers. They have lots of knobs. You fiddle the knobs to death, and if you get good results, you declare success. A few years ago, people tried to take ideas from differential equations and dynamical system and graft them onto neural networks, or say, geez, I can interpret these things as dynamical systems. If you go back, a couple decades ago, this was in fact went the other way. Oftentimes you thought about these as a dynamical process that then you discretize. So what's the relationship between the two? And is it the case that some of the recent work that says it's continuous, is it continuous in the sense that would make a scientific computing or a numerical analyst happy? Someone that works with numerical methods and integrates forward PDEs in time? And I think the answer is an unqualified no, but you can use a little bit more sophisticated numerical techniques and get models that meaningfully are continuous in depth. And that has a range of good properties in terms of stability and in terms of properties at inference, as well as training. So those are the, this is sort of the high level point. And as David said, if there's questions, post them in the chat box and he'll ask them interrupt at some point. So to just put a little bit of a picture on sort of some of the stuff I've been saying, I mean, machine learning tends to be fairly data driven. Oftentimes it's black box. You don't know what's going on in the model. This was true years ago. I mean, I did work on interpretable low rank approximations years ago, which is an interpretable form of SVD, because people used to say SVD and PCA are totally non-interpretable. Now neural networks are so disastrously non-interpretable that people say PCA is interpretable. So black box means different things, but black box, it's hard to interpret, it's hard to rationalize or reason about. May be very expressive because they can approximate any function in a class, but that may have downsides too in terms of generalization. Dynamical systems is sort of a very different thing. Typically, you peek inside, you know what's going on, you're interested in robustness or stability properties, how noise enters in is in a very different way. And so we want to get some sense of what can we learn from dynamical systems and control theory applied to ML and vice versa. So our residual networks, do they meaningfully you view them as differential equations? You run a training process. What are you doing? Are you optimizing a function? Are you trying to perform some sort of optimal or suboptimal control? Are you cooling down a temperature parameter? So we're trying to understand these things in a little bit more principled way. We've done a range of things. Most of this I'm not going to talk about. Some of it's, as I said, taking ideas from ML and just grafting on dynamical systems. Some of it's going vice versa and going the other way. And we're going to want to try and talk about some things that tie the two together. And as an example of connections between, in particular, deep learning, which is, as you know, subset of machine learning, but something that's gotten a lot of attention recently. The essential building blocks of residual networks are these so-called residual units. And so you basically feed data in and you run through 10 layers or 50 layers or whatever. And you say the state at the next layer, is the previous plus maybe some update. And the function sigma that denotes the Tth residual module, which is a basic building block, maybe with parameters, a nonlinear map. It might involve truncation or something. It's parameterized by a set of parameters theta. And if you just consider the basic residual unit, xt plus 1 is equal to epsilon xt plus something, call it ax xt. Then if you come at this from dynamical systems, you say, oh, I mean, that sort of looks like a differential equation, or maybe a discretization of a differential equation. So is this true? And there's been a lot of interest in this. I first saw this a few years ago, and I wondered, is there something meaningful there? Is this sort of a syntactic relationship that isn't so fruitful? And a lot of people said, well, we can develop models that are continuous, neural ODEs and other things like this. And so we got to think about this because we noticed that a lot of these models were very unstable in a way that continuous dynamics should not be. And so we went in that and looked in a little bit more detail. So what can we learn from dynamical systems theory? Dynamical systems theory has time. right? I mean, that's the point of it. You have a dynamics. And so time is a first-class citizen in a way that it's not in the structure of machine learning theory. Stability theory plays an essential role. If you train models, neural networks in particular, and you tweak anything about them, hyperparameters, this, that, they become wildly unstable. And that may be an evolution. Model space, that may be an evolution of data as you feed it through. And that seems sort of awkward because you typically would want, if you want to extrapolate, if you want to port to tomorrow's data that might be different. In machine learning, they call it transfer learning. In science, you'd call it extrapolation. You want some sort of stability in the model qua model. And so one way to characterize this is with Lyapunov trajectories. And so we'll see that for these RNNs, stability matters, and it can manifest itself in a different way. And you got to be a little bit careful here. I mean, if you don't know about all the structure, what's going on with these models, think about the power method, right? The power method, you take a vector, you multiply it by a matrix, you scale that new vector to have norm 1. If you scale it to have norm 1.1 or don't scale, the norm blows up eventually. If you scale it to have 0.9 or don't scale, depending on whether you happen to be above or below 1 when you do the matrix vector multiply, if it has magnitude 0.9, it'll shrink down to 0. So you don't necessarily want to have small or large values. You may want to be right at a critical point, a transition point, where gradients, in the lingo of neural networks, gradients don't vanish or explode. And so this will be critical for what we'll get to later. And another sort of final high-level comment is sort of how do you want to integrate prior physical knowledge? Take from the other side, how would you want to integrate knowledge into a machine learning model? So one way, I'm calling it option 1, and I have a typo here because they're all called option 1, so this should be 1, 2, and 3. You could design an architecture to be a physics-informed architecture. I'm doing climate science. I want an architecture that satisfies certain invariance principles or something. And that's sort of what happens in machine learning. I mean, I know that images should have certain symmetry properties, whatever, so I designed convolutional layers to have that. I know that language has some linear structure as I march along sentences, so I designed transformers or something that may capture that in some way. So ML, a lot of it's shifted from sort of, let's call it feature engineering to architecture engineering, where you put domain insight into the architecture, and then you just press a button and try and do a search over hyperparameters. So you could do physics-informed architecture. You could do physics-informed regularizers. You could have an objective, in equation 5 here, some loss, and it's f plus lambda g. G is an L1 or an L2 or something. So you tack on some regularizer, and there's a lot of ways to do regularizers. There's an important subtlety that is worth pointing out, that if you incorporate a regularizer, in some ways the objective, f plus lambda g, is going to be equivalent to minimize f such that g is a constraint, and it could be an equality or an inequality, that doesn't matter. So these two in some sense are equivalent, but that's sort of in a very structural sense, in the sense of convex optimization, the value of the objective, not necessarily the solution certificate. As a practical matter, they're very different. They're not, that equivalence is not robust to epsilon approximation. And so, for example, if you're epsilon close to one solution, not necessarily for the other. They can be very, very different. There's an ill-opposedness there. And so if you don't know a lot about optimization, linear algebra, think about like a ridge regression or a Moore Penrose inverse. If you have small eigenvalues, the two become very, very different because the pseudo-inverse of the small eigenvalues blows up. At 0, they may be more similar in some ways. So there's an ill-posedness there. And so similarly here. And the way you typically do this in machine learning is you say, you adopt this Lagrange formulation. I want to optimize f. I'm going to add a soft constraint plus lambda g, and I apply low precision stochastic gradient descent to approximate this very, very, optimize this very, very approximately. And that's fine for certain problems. For other problems, it's very bad. So if you have a physical model and, for example, you want to conserve an invariant like energy, if you conserve energy only approximately, and you run this thing forward as a dynamical process, your energy blows up. And so you may want a hard constraint. And so you really should do something like a second order method or demand that you satisfy a hard constraint. For every one paper you see here in machine learning, you see 1,000 papers that do this other thing. So that's, these sort of little details would matter a lot. And so that's sort of under the hood of what we're talking about. All right, so let me first talk about physics-informed autoencoders. I'll get to continuous in depth. Let me pause for a second and see if there's any quick questions on general motivations or objections, or if everyone's reasonably happy at this point. All right, so I'm not hearing anything. So with luck, I haven't lost anyone, and everyone's sort of reasonably happy. So let's assume that. So Lyapunov stable fluid flow prediction. So the goal here is going to be to do physics informed learning. Supervised ML aims to learn a model. We want to cook physics in some way, and we could be doing climate science. We've looked at that. Fluid flow, fluid mechanics is a canonical example that's very challenging because there's properties going on at a range of size scales. And if you want to go and have ML touch industry beyond, a handful of internet and social media companies, you may want to design better, cars, not self-driving cars, although that could be interesting, but cars or airplane wings or something like this. You want to understand how the fluid behaves over it. You can do this in a PDE sense, but maybe you can do a better job in certain ways by incorporating ML models, not naively, but integrating them well with the domain science. So the setup is we're going to want to do fluid flow prediction. There's going to be a dynamical system of interest, and we're going to model it as x of t plus 1 is some transformation, call it a of x of t plus some eta noise process. In a data-driven setting, we might have access only to the high-dimensional observations. So, we see some observations. We don't know the underlying dynamics. So the question is, given a sequence of observations, we want to learn a model that will map from one time step to the next. Sort of an important subtlety is, if I give you these data points, the first thing an ML person would do is to randomly split these into training and test. Whereas for most of the motivating fluid flow and scientific applications, you'd want to consider the first half, split this into training and test, and then split or predict on tomorrow's data. And tomorrow's data is going to be different than today's. That's the point. It's not the usual training test. That's not a random split, but that's what people are interested in. And they want to predict not 1 or 2 days, but they want to predict 3 or 4 days ahead if they're doing weather, for example, or some number of seconds ahead instead of milliseconds or microseconds. So they really want to extrapolate in some sense. So a physics agnostic model, given a bunch of data points, write down an objective, minimize the mean squared error. During inference time, you want to obtain predictions, typically not of f, the learned model applied to y, but of f composed with f composed with f applied to y. So you want to iterate it. So if you're off by just slightly, like in the power method example, this will explode or be ill-posed. Typical Blackbox model, the way people want to use this is they want to have some sort of automatic structure. This is working its way. Techniques from scientific computing like automatic differentiation are slowly working their ways into these models. We want to look inside a little bit. So the improvement I mentioned that we have here that I'm not going to talk about uses ideas from Koopman theory, which says that you can model a nonlinear system as a linear system in some transform space that you don't know the transformation. We had sort of a proto-Koopman, a pre-Koopman version of this here. We said, imagine that the model, the architecture is an encoder. You have some dynamics, maybe with a skip connection because of the residual thing, and a decoder. So you're going to take the snapshot. You can think of this as an image of a fluid. You're going to encode it in some way, run a dynamics, and decode it. So if you want to iterate, so that's fine. You could do training test errors and you'd get something. If you want to iterate this process, iterate the dynamics more than one step, a reasonable constraint is to say that psi and phi are inverses or approximate inverses. So you could add on a regularization, your objective plus lambda, y minus hopefully an approximate inverse, y. Just tack that on as a regularizer. So that's something you could do. You could also say, and that does okay. You could also say, well, I want to explicitly encode some stability properties, not just a one-step dynamics, but a multi-step dynamics. If I want this to iterate this many times, k times, I might try and cook that into some other regularizer. So now we're adopting the pathway of a model. We're going to tack on regularizers with the soft Lagrangian formulation. What form would that take? So that's the question here. And a reasonable form is going to be the following. So you want to employ Lyapunov stability ideas. And if you have a dynamical system, you say that it's stable. There's a couple different notions of stability here, but let's say it's stable if all trajectories starting pretty close to the origin remain arbitrarily close or very close. If the dynamics are linear, you can check it with eigenvalue analysis. If they're not, it's going to be a bit more complicated. So this is Lyapunov stability ideas. So in particular, Lyapunov's second method will state that a dynamical system will be stable. So A is the dynamics that we may be wanting to learn, is going to be stable if and only if the following condition is satisfied. If and only if for every symmetric positive definite matrix Q, there exists a positive symmetric definite matrix P such that A transpose PA minus P is negative Q. So this is just a condition. If you've seen dynamical system theory, and you may know where this comes from, and if not, it's just a condition I need to satisfy on the matrix, the learned model, the dynamics A. And so you could say, well, I want to choose the right eigenbasis, and I want to impose that the symmetric matrix P, choose the right basis, that the matrix P defined in this expression, omega, remember that's the learned dynamics, P omega minus P is negative identity. So this is what we're going to work with. And we're going to want to consider the case where omega is diagonalizable and Q is chosen as an appropriate eigenbasis, in which case omega transpose P, omega transpose P omega minus P is a negative identity. And this, if we have the right diagonalizable and eigenbasis, this is just a constraint on a bunch of numbers. Omega I pi omega I minus pi is equal to -1. So remember, this we want this to hold for every p. We want this as essentially a constraint on omega. So what you'd have is you'd want a discrete time Lyapunov function that, well, what it is, it will look something like this. If p is larger than 1, the values of omega are always going to be less than 1. Nothing if p is between 0 and 1, and if p is negative, it behaves this way. So if you're slightly negative, the value is very large. If you're very negative, it's sort of small. So think of this like the cusp of the power method when you're right near 1. And this will diverge in some funny way when you're very close, but far away, it may be okay again. So this is a critical regime here. And so just pictorially, I'll give you a functional form on the next slide. Pictorially, a stability and promoting prior is the following. If p is greater than 1, just set it to be 0. And if p is negative, penalize. Tack this on as a soft constraint and penalize. And if p is slightly negative, penalize more. And if p is very negative, penalize less. So this is what we want. This functional form is not, this particular shape isn't forced on you. I mean, you could have penalized more aggressively or less, but this qualitative form is what we'd want. And so a function that would give you that qualitative form is if p is less than 0, exponential of p minus 1 norm, absolute value, over gamma, and 0 otherwise. This will be the particular one you have here. You could choose a different functional form. We played with a few and you got similar sort of results, but this did best, so we stuck with this. So you could use a different one. But the point is you want a functional form here. And then you just tack this on minimize f plus lambda g plus kappa g prime. This is the interesting objective because from there's no reason from an ML perspective that the static and time that you come up with this objective. This isn't an L1 or an L2, it's just some peculiar thing. But if you think about hello world dynamical systems, this is this or something like this is forced on you. So we thought it was sort of interesting for that reason. All right, so we want to have a learned model. We adopt the soft Lagrangian formulation. We came up with a regularizer that you would have never thought of otherwise. You could also tack on an extra regularization to say phi, plus omega times omega. So regularize a 2-step penalty, or 3-step or 4-step. Now, this I wouldn't say is particularly satisfying, but this is, I think, the usual MO that a lot of people that have just come from machine learning think about. Just tack on more regularizers, tack on more parameters, and do a hyperparameter search. And this, depending on the details of the setup, either helps slightly or hurts slightly. But sort of for a point estimate, it may lead to a less robust model. That's a different issue, which we'll get to in a second. So we looked at flow past a cylinder. We looked at daily sea surface temperature. In this case, in the Gulf of Mexico, we've looked at various climate processes in the Pacific and other things here and elsewhere. And just in the interest of time, I'll show you a few pictures to illustrate what's going on, to illustrate the qualitative point. The left plot is error on the y-axis, up is bad, and time steps forward. And so the red is the physics-aware model, where we cooked in that domain reasonable regularization term. And the blue is not. So the blue says you can, predict 1 or 2 steps ahead, but if you do more than about a half dozen iterations, you do much worse. Red, you can march ahead 100 steps. You'll eventually break down, but not, but you can march ahead 100 steps and do pretty well. The reason this works is you have an eigenvalue here outside the unit circle. It's just slightly outside the unit circle, But if you add the regularization we added, you can pull it in. Now you could say, what about other things? Why do I need to do this? Could I just tack on a ridge regression? It's called something else with weight decay and with machine learning and neural networks, but it's essentially a ridge regression. You could do that. That's a very coarse control parameter, and you do other damage to the system. So this is a more precise way to do that. It's a more precise control parameter, essentially, that really focuses on the dynamics rather than just whacks it with a very coarse tool. More results on flow past the cylinder. Here the details are a little bit different. The physics-aware model stays with low error. The physics-agnostic one gets much worse. Change more parameters, and you get the same results. So depending on the details, you're either much better or moderately better, but you're better. You can apply the same thing to sea surface temperature, which is a much more realistic thing, and you see the same sort of thing. The physics-aware model does better. So we could push on this in some more detail. Here the instability is much more prominent because the eigenvalues are much farther outside the unit circle. You notice, interestingly, you pull them much farther in. This is actually not necessarily a good thing, and I think that's why the red's actually doing a little bit worse. But you could say that's future work, or you could take a step back and say, really, we're adopting the usual MO here, and that's less interesting than cooking in Koopman operators in a more refined way, or doing, handling the continuous properties in a more refined way. So I could go into more details on here if anyone's interested, but let me just sort of transition at this point. But just to say that this is a tip of an iceberg. I think the lesson we took home from this was that you can adopt the usual MO, but things get fairly complicated in terms of hyperparameter fitting, and you may get models that are less robust and less stable and have other issues. So, so let me shelve this for now. Oh, there's some more pictures of the sea surface temperature. If you're a climate scientist, you know what this means, and if not, not otherwise. But so to summarize the second part, physics-informed autoencoders, and there's a lot of work sort of going on in the last few years doing this, they can help improve generalization performance. And in particular, they can do it in a more precise way than whacking the model with essentially a ridge regression type objective. The problem here is that you're starting with an objective F, and you replace it with F plus gamma regularization, maybe plus kappa regularization, maybe plus some other parameter times regularization. And now you're cooking in structurally a much more complicated model. You're going to have to hyperparameter search. You may get very, very fine point estimates. So in certain applications, that may be the right way to do it, especially if you're feeding it into an ensemble of models to do forecasting and internet analytics or something. And your sort of control parameter on the stability of the system is something else. Certainly, I think this is dissatisfying for a lot of scientists who want to get some sort of insight into how the model maps to what they know about the science. So a range of other extensions and next steps that, as I said, I can answer questions, but I'm not going to go into in detail today because I want to switch gears a little bit. I wanted to switch gears to talk about the continuous in depth, because I think this is of interest by itself, but it also is connected with some of the things that are a little dissatisfying about just tacking on more regularizers with the physics-informed autoencoders. So let me pause for a second again and see if there's any questions or if people are still reasonably happy before I shift gears and talk about the continuous in depth models.
I don't see any questions in the chat yet.
All right. So I don't know if that's a good or bad sign. I was teaching a class last spring, and as some of you probably were, I had to shift online very quickly. And so as you know, you can't always tell if no questions are good or not, but I'll assume the best. How about that? All right, so let me shift gears and talk about continuous in-depth neural networks. And I should point out, Ben Erickson's sort of the postdoc with me. He's led the charge on this and a range of other things with Dynamical Systems. Mickey Muhlenbach was involved with the physics-informed autoencoders and some other things I'm not talking about. Alejandro Kierga and Dane Taylor were working on the continuous in-depth neural networks. And Alejandro was, I think, at LBL at the time and is at Google now. So he has sort of an interesting perspective on both sides of the fence, as it were. So let me tell you about what we were thinking here. What we really wanted to do was not say, here's a big infrastructure of PDEs and tack on one little one little neural network thing, and not say here's a big neural network model and tack on a physics regularizer, which is what we did before. We want to understand, can we get a stronger connection between these two? And the way to do this seemed to be to think about ResNets. So ResNets are popular neural network architecture. Pictorially, because I think machine learners like these sort of pictures, they look like the following. They look like you have some state xt, you feed through a residual unit. You may have these connections here. The difference is that either xt goes to xt plus 1, or the residual unit sort of computes a delta, like a state tomorrow is state today plus a delta. And oftentimes that gets better results, which, if you know numerical analysis and other sort of things, that is maybe not surprising. So recent work notes that ResNet, in some sense, looks a little like forward Euler discretization of a dynamical system. So if you say x of t plus 1 is equal to x of t, plus I snuck in a delta t here, residual unit. That sort of looks like a discretization of a dynamical system. Now there's no delta t here, so I sort of snuck that in, but fine. And then you say, well, go to some limit, and this becomes a differential equation. So is this correct? Is this meaningful to say this? So certainly it's algebraically correct, it's fine. But is it meaningful to say this? And the spoiler is going to be, I think it's fair to say that ResNets just aren't forward Euler discretizations of dynamical systems in any meaningful way, essentially due to overfitting. And this is related to the fact that Euler is a relatively weak discretization method, where the discretization error is sort of on par with, they call it data error or machine learning error. The delta t here is a little bit of a red herring, but the point here is that the usual way you would evaluate models is training and testing error. You never really ask counterfactual questions. You never really ask questions about how the model behaves after you train it, except in a training and testing error sense. That's very different than if you do scientific computing and you think about discretizations of integral operators or of differential equations. Think about discretizations of them. You develop a discretization, but you believe there's a continuous thing under the hood, and so you could discretize to higher order. You could discretize to half the time step, and you might say, I want to know how my model behaves as delta t goes to 0. And if I'm meaningfully a stable discretization of a continuous underlying dynamics, the model should behave in a very structured way as delta t changes. So you could ask similar questions here, and we'll see that the justification for the spoiler is that when you do that, you get different answers than you might sort of naively hope. So experiments in dynamics, what does it even mean to say that ResNet learns a forward Euler representation? So there's an algebraic syntactic similarity, but what does it mean to say that it learns a continuous dynamical system? So to start, let's go to a context where a dynamical system is meaningful. And so like we've been talking about climate data or flow data or so on. And so to work in a very structured environment, let's work time series prediction of a dynamical system. We need to be slightly more complicated than a linear harmonic oscillator. So let's go to nonlinear harmonic oscillator. It's going to be basically second derivative of x is equal to sine of x. So this is not linear. It's sufficiently nice that there's a closed form solution for it. So we can compare against that closed form continuous model, and we'll do that. And so we're going to learn a model, and we're going to say, how close are we to that thing we learned? And what if we change the numerical integrator? What if we change the time step, et cetera, et cetera? Do we behave in the way we'd expect? And before I get into the details, just keep in the back of your mind, numerical integration theory, as it's usually instantiated, comes out of scientific computing, where you have an underlying dynamics. Machine learning, comes in the opposite direction. If you have an underlying dynamics, then you say, how do I discretize it to get some order of approximation or whatever? Machine learning, you're just given the data and you're backing out of dynamics. And so you're really coming at it from the other direction. So it's not even clear that this approach we're taking makes sense, right? But we'll see that it does give sort of meaningful insight into things. But you're really coming at it again. So we're applying it here to a dynamical system, but we're going to want to ultimately apply it to things that are not dynamical systems, where I just give you data. You might hypothesize there's a dynamical system there, and that may or may not give you better results, but there's not necessarily. All right, so revisiting the simple dynamical system. So learning a residual in future is today plus update. Let's study training a model f of x based on a neural network, call it G, where x of t plus delta t is equal to f. It's equal to x of t plus g of x of t, which is basically a numerical method update. Numerical integrators are going to approximate this integral with a discrete series of applications. a discretization of f of x as the derivative. So x of t plus delta t is equal to x of t plus some numerical integration scheme. Right, so this is a neural network, this is an integration scheme. Syntactic similarity is not going to be sufficient. So approximations to dynamical systems have a richer structure than just that syntactic similarity. For a given integrator, if you make delta t get small, and that's 1 over the number of layers in ResNets, error goes to 0. Do we see that? This is like time-step refinement. Integrators have a rate of convergence. The log of the error, log of delta t, you get a slope of r. And if you know RK4 is better than midpoint, better than Euler, that means this R decays gets smaller faster. You know, you do a Taylor series expansion, you cancel out terms of different orders. The same dx dt with different integrators should approach the same solution at their respective rates. If I wanted to do midpoint and I wanted to do RK4, I should approach the same solution, but maybe at a different rate. So we can ask these questions and we can try and verify them. So we're going to hypothesize that this makes sense and we can try and verify them. So these conditions are critical in numerical integration schemes. They can use integration tests for software. We're going to apply them to things that are purportedly continuous machine learning models, continuous neural ODEs, for example, and ask the question, are they continuous in the sense of the word? So does ResNet satisfy these properties? So if yes, we should be able to alter the model, the number of time steps, the numerical integration scheme, and we're going to get these properties we expect. If no, then the model should just do whatever. I mean, go haywire, flatten out, behave differently, but not what we would expect. All right, so we can do this. So what we're going to do is the following. We're going to make a data set with a given delta t. We'll run it for some number of steps. We're going to train 3 models using different Gs, shallow tan H with 50 hidden units, let's say. The details here don't matter. We could have done the details a little bit differently. Then we're going to freeze G. So we've learned a model, we're going to freeze it. Just done, right? So we're not training a million times freeze it. And the hypothesis is that A, B, and C, I think they were called A, B, and C on the previous slide. Those 3 conditions should hold. And so cut the time step in half. How does it behave? Change the numerical integrator. How does it behave? So we're going to learn 3 models. One is going to be based on a forward Euler discretization. X of t plus 1 is equal to X of t plus delta t g. During training, this delta t is 1. When we're evaluating it, we could choose delta t to be something different. Midpoint is going to be that where we have g of x of t plus delta t over 2g. So if you're familiar with the midpoint rule, this is the midpoint rule. RK4 is going to be that, but you have sort of an extra step and you have the weights. I'll put them up in a few slides, but you'd have all the weights you'd expect to get the order of convergence you want. So we're going to train 3 models. One uses a ResNet-like structure that's basically that with delta t equals 1. One's going to have a ResNet-like structure, but then each side, each model is a little bit of other stuff to look midpoint-like. And then one is that where inside each stuff is something more complicated to look RK4-like. For ground truth, we're going to use the analytical solution and we can plug in the known dx dt into the integrators. So after we train the models, when we train the models, they all do well. So they're all good discrete models. All right, so by the usual metrics of training and test, they're all good models. So the orange here is numerical Euler. It's not a learned machine learning one, it's numerical Euler. And it does well for about 1 cycle, and then it just does poorly. So here is rho, here is v. These are position and angle variables. And so it just does poorly. And if you know about Euler integrators, it's just not a great integrator, and so that's why it does poorly. All the other ones, the blue, the green, and the orange are on top of each other, so you might not even be able to see the differences. All right, so they're all good discrete models. We could do training and testing error. You could evaluate it as a function of the number of oscillations here. So they're good discrete models by the traditional ML sense. If you cut delta t in half, the first thing to notice is that the orange gets better. The Euler integrator gets better. It'll eventually go haywire, but I get more oscillations, and I'll get more oscillations here. The next thing to note is that the blue and the red are ground truth in RK4. The blue and the red are still on top of each other, but the green is the Euler model, the Euler neural ODE, starts to do worse. So what you're saying is I'm cutting the time step in half and I'm doing worse. That should be the first sort of signal that maybe something's problematic. So rather than going into more detail on this, which you could, let's do sort of a much more exhaustive scan, if you will, of this as a function of various parameters. So for any one point here will correspond, for any one plot here, this oscillation plot, will correspond to 1 point on this curve, on these one-off plots. So one-off plots really aren't sufficient. Let's sweep delta t, let's calculate errors. So let's look at the left-hand side here first. On the left-hand side, what we have is y-axis is error, down is good. X-axis is essentially the time step. So smaller time steps to the left. Time steps is 1 over number of layers. So smaller time steps means you have more layers. So you shouldn't think of this. One way people think about dynamical systems when they do apply it to machine learning is like the dynamics is SGD. And so if I run 10 or 100 or 1,000 steps, I'm propagating forward in time, 10 or 100 or 1,000 time units. Don't think of this that way. Think of this as I'm integrating from 0 to 1. And as I have 10 or 100 or 1,000 time steps, I'm getting a final resolution of 0 to 1, which is what you do if you're integrating a function on the unit interval. So the first thing to note is here is marching from large delta t to small delta t. Forward Euler black has a slope, midpoint has a slope, RK4 has a slope. These are just the slopes you'd expect. It's those R values. The next thing to note is that at delta t equals 1, all the models are pretty good. The error is 10 to the minus 4 for Euler. It's pretty good. The error might be slightly better for midpoint and RK4, but don't read too much into that. That's, they're all good. They're all below 10 to the minus 4, which is well below the machine learning sort of level of errors. They're all good discrete models. As you change delta t, cut it in half or in a quarter or an eighth, the model gets much worse. And so this is what you saw on the previous slide. If you increase it, it gets much worse also, but that may be less surprising, but it gets much worse. At large time steps, the red, the purple, and the blue, roughly follow the corresponding integrators. For Euler, it gets much better at delta t equals 1 and then gets worse. So you really have a spike here. If you change delta t at all, the model gets much worse. This is a wild instability. For midpoint and RK4, the discretization order is a couple orders of magnitude less. And so you're very smooth through this delta t equals 1. So you learn the model at 1, you apply it at delta t, a factor of 2 above or below, you get basically the same answer, slightly better, slightly worse, but not a wildly unstable situation like you learned here with Euler. So on the right, you could say, well, don't just vary delta t, try different integrators. Learn a model. Remember, we learned 3 models. We learned RK4, midpoint, and Euler. Take the model you learned with Euler and then use it at evaluation time with a different integrator, not necessarily a different time step. And what you see is that if I take Euler and put it into, and then go to midpoint, go to RK4, you do not see up as bad. Remember, down is good. The red is bad. You basically see what you'd see here on the red, right? You're much worse than Euler and RK4. So when you train to this not good model, it's good discrete, but not good continuous model Euler, and you use other more sophisticated integrators, you don't do better. You do poorly. But if you learn the blue here, if you train to midpoint and you go to RK4, you don't do better. But if you go to Euler, you do correspondingly well with midpoint. And so the purple's here and here. And if you work on RK4 and then you afterwards use a midpoint and an Euler integrator, you do exactly as you would expect, the same as Euler or midpoint would do. So if you change time steps, you see this strong instability at delta t equals 1. If you plug in different integrators and you go from less sophisticated to more sophisticated to less sophisticated, you get what you sort of expect. So this really says that these are good discrete models, but Euler is not a good continuous model. But this and other evidence shows that if you train to a higher order integrator, you can get something that's meaningfully continuous in time. So these slides are on my web page. And so I have a bunch of sort of slides here with arrows that walks through in some more detail what I said. All right, so the implication. So the results show that I think the prevailing training MO that people adopt, which is cut in half, train, test, backprop, the usual thing, does not yield models that can meaningfully be interpreted in terms of continuous theory. Having a peak that is fragile to the number of time steps essentially means you're solving a poorly posed problem. And that's, in scientific computing, first question, are you solving a well-posed problem? If the answer is no, go home. Don't solve it. Formulate a different problem. That's why you do ticking off regularization and other things like that. Here, there's so many control parameters and knobs, and people evaluate based on training and test and not much else, not domain-specific insight, not stability, because there's no reason that you'd have to solve a well-posed problem. There's a lot of problems in computer science that aren't well-posed. So having a peak says that the model is fragile to the number of time steps, maybe other parameters like the details of the input data, et cetera, et cetera. It is fragile with respect to those things too, although I didn't show it. So this means you can't really do interpolation. You can't meaningfully say, I have a ResNet 50, what do I almost have a ResNet 51? Or do I almost have a ResNet 25? You can't, do this sort of, do I almost have a ResNet 100? You just can't do that. If you had this continuity with respect to time, a number of layers, you could do that. You could change the number of layers after the fact. You could do other things like that. So we'll get to that in a second. The RK4 scheme, basically the discretization error is so much less than the, call it data or machine learning error, that you can do this. And in some cases, midpoint 2, in the cases I was showing you midpoint 2. This means that you can go to change the number of layers during training and inference and a range of other things, but it meaningfully provides a way to interpolate. It's meaningfully continuous in time in a much stronger sense of the word. And so you can view this in a range of ways. The analysis can be seen as a diagnostic tool to assess if the model's overfit. How well does it represent a continuous system? Now there's a question here, why do you want a continuous system? You don't necessarily. There's a lot of times discrete models are good. There's a lot of interest recently in continuous models, and there's claims made, and I think if you really do a careful analysis of using ideas from dynamical systems and numerical integration theories, those models really aren't continuous systems in a strong sense of the word. If you're modeling a dynamics, if you're modeling something physical, you probably do want to respect that. That's like a slightly more fancy version of I want to conserve energy, because if I don't conserve energy, my thing blows up. So you might want to actually have a continuous model. And then since you got to work with a discrete model, I actually want a discrete model that's meaningfully an approximation to a continuous model. There's other cases where you don't necessarily want that, but you may want a good discrete model and none of this is relevant. Or you may say, geez, I want to have a discrete model that's a good approximation to a continuous model, just because it provides some robustness or stability. And so I'll show you an example of that. But that I think is where some of these things are particularly relevant beyond just the connection in scientific machine learning. So by a range of other measures that I'm not going to have time to talk about, the RK4, the Hessian landscapes are smoother here. It's a bit choppier. By a range of other methods, just as a plug, it's a sort of a pet peeve because people, a different talk I could have given is add a Hessian. I'll be giving a talk next week on add a Hessian. First order stochastic optimization methods are very popular in machine learning. I think because they're easy to use. They don't perform particularly well, so you need to introduce atom and addigrad and this and that and add lots and lots of momentum, lots and lots of parameters and hyperparameters, and then you got to train those hyperparameters. When you train those hyperparameters, you end up in a situation like with that spike I just showed you. End up with a model that does well as a point estimate, but is extremely unstable and ill-posed in other ways. And so if anyone says don't use second order methods because you got to invert a Hessian, you should walk out of the room and go home. If you know numerical analysis and scientific computing, there's a rich literature on matrix-free methods and approximate solves and this and that. And so if you want to do scalable second-order optimization on state-of-the-art methods, you can do that in roughly twice backprop time. No storing billion by billion Hessians, twice backprop time. And the models become much more stable and robust. So that's another talk, but just sort of as an FYI. And a lot of the themes we're talking about here would apply there. I want something that's robust in ways that SGD wouldn't, solve, because you'd solve a ill-posed problem. And that's not an issue with SGD. That's an issue with the heavily parameterized SGD. We saw the same thing with KFAC, which is sort of an approximate second-order model, but has a lot of hyperparameters. So it's the introduction of all these hyperparameters that are then hyper-tuned and evaluated based on training and test curves that leads to these instabilities and difficulties with interpretation. So continuous in-depth networks. So ContinuousNet is a deep model that is a discrete approximation to a continuous dynamical systems. Choose basis functions in depth for parameters, use a higher order midpoint or RK4 scheme. You can do time step refinement and grid refinement. And the goal is basically recover and extend the same graph as ResNet if you chose Euler in a very special case, but as a function of time that's much richer. And essentially it's a plugin. You can just plug in a different ODE block. That's the idea, and we can do that. So ContinuousNet's governing equation is x dot is equal to epsilon r of x, residual blocks of residual units replaced by numerical integrators. And then you'd assemble them in the same way. There's a couple subtleties about normalization that I'm not, batch normalization between layers and whatever, but ask questions, or I can point offline. But I think this is the tip of an iceberg, and there's a lot of other ways you could do it. You could use implicit time stepping. You could use Verlet type techniques. So I'm just talking about the hello world here. Importantly, this R is a function of x of t and theta of t. It's not a function of x and theta and t. So the time enters only through x and t. So the parameters are functions of time. And what that means is, I guess I have in a few slides, we're going to get something to be continuous in a much stronger sense of the word, but it means that the parameter theta is going to be a function. It's going to be continuous. And so we're not going to be able to learn it, but we're going to learn it represented in some basis. In the neural network perspective, the integrators are just prescribed graphs. And so I could have ResNet Euler where I have this box. I could take midpoint where I have the box and I chain it together with a delta t over 2 and a delta t. RK4 chains things together in this way. RK4 3/8 does it in this way. These delta t over 3, these are not learned. These are given from on high, because these are the ways that you get cancellation of errors at the order you want in numerical integration theory. And again, here's some more dashes to illustrate a few things. So I could have Euler at one depth, I could have Euler at another depth. I have this more complicated graph, but this particular set of edges is the one that gets things to cancel in a way that gives me this continuity. All right, so picking a scheme and an NT a depth. So basically I want to choose a depth, 3 or 6 or 100. I pick a scheme, which is this block or this block or this block, some other blocks. And there I'm learning a parameterized family of models that really are meaningfully discrete approximations to a continuous model. As I said, the basis functions theta, I have to learn, because now they're functions, I mean, really honest, to God, functions. So theta is a linear combination of some basis functions, and so I have to learn the coefficients of that basis expansion. So I do it the usual way with backprop and everything, but that's how I represent the functions. You can imagine there's a whole line of work on figuring out the right functions for the right problems and so on, and we have some examples of that, but this is opening the door for that. But it allows us to answer questions, what's the value halfway between time steps, which, the flip side of that is, what if I added one more layer or double the number of layers in my graphs? If this function theta is a bunch of step functions where each theta parameter value corresponds to one particular layer, then you get the usual ResNet. But the point is, you don't want to do that. You want this function to couple the layers together, so you get this continuity in time. So experiments for image classification. So before we said, here's a dynamical system, it's a hello world. In the last few minutes, I just want to show the same plots, but written in a way that's more familiar to machine learners, applied to image classification. So we said before, the original hypothesis was that convergence can be used, you can apply a convergence test. So let's apply it here, and would expect forward Euler to overfit in some sense, and to get a model that's poorly posed, and would expect RK4 and midpoint to do better. So this plot here is, on the left, let's go, is the test error, down is good. And on the x-axis is the computational graph depth, the number of layers, which is 1 over the number of time steps. So here I'm plotting, and there's no logs here. I should have pointed out the previous one was log. Here it's not. This is the same plot as that previous one. I'm doing a plot in the language that ML people would think about. That was more familiar with people that knew scientific computing and numerical integration, but we're plotting essentially the same thing. The only other difference is we don't have the ground truth solution here, so we use the test error as in place of the analytical solution. Can train ContinuousNet 32, 32, 32 with RK4 and Euler, left half. So look at blue. Blue goes down at 32, you hit a minimum, and it goes up and up and up and up. So basically, we ran the same experiment before we trained the model, and then we varied the number of layers. And it does very well here, but it gets not so good at other values of depth. If you did this with RK4 Classic, it goes down, it levels off, it's about the same, and then boom, it just flattens out. Now question, do you care about that little 0.1% there? Right there, you see blue is slightly better than orange. We could have probably squeezed this and been slightly better if we wanted to say we're slightly better, but that's not the point, whether we're slightly better or slightly worse. All of the 99% of the work in ML focuses on how blue is just so much better than orange here, because it's 0.1% better on a test error. And for some applications, that's very important. But a lot of people would say blue is just wildly unstable. There's no connection between depth 32 and depth 33. I can't double or cut the number of layers in half, which I can do with the orange because I'm meaningfully continuous in depth. I can interpolate between layers. In the same way as before we trained a model and we applied it after the fact as an integrator with a more sophisticated or less sophisticated integrator. We trained Euler and then plugged in RK4 or midpoint, and we trained midpoint and plugged in RK4. We would do the same thing here. You can do Euler to RK4, it goes down, but it's very unstable. You can do RK4 to, well, the other RK4 classic to 3/8. You can do RK4 to Euler, it goes down and flattens out. So the purple is RK4 to Euler, and if you go classic to 3/8, it levels off in a stronger way. What you see here is the purple just gets better very gradually and then levels off. I could change the number of depths if I want. So now I have arrows just to go into a little bit more detail. Same thing with CFAR 100, same thing with Tiny ImageNet, same thing with a range of other things. So why ContinuousNet? Let me look at the time. Okay, so 2 minutes. So many programs exist for the same problem. Essentially, we're choosing one. We're hypothesizing that we want a continuous model because it has better stability properties. And there's many equivalent graph manifestations, number of layers, the particular integrator you use. And I think it opens the door for a better understanding of a lot of post-training and during training tricks. So for example, 2 things that we're looking at. During training, I could say, well, I want to, let me skip some numbers in the interest of time. I might want to say x-axis here is the training time and y-axis is the clock time, training time meaning the number of iterations. I can change the resolution during training. This is like mesh refinement. I can change the number of steps during training so that if I want a coarse model, I can use one method, RK4 classic, and then I can refine that over time and get better refinement later on. And so there's a trade-off space here depending on how you would want to perform just during training. You don't care about robustness. You don't care about any of these other things I'm talking about, just better training. So, this opens the door for something like that, and we're actually looking to that. And then during inference, I think I pulled the slide out, but the toy example during inference is, I want to train a big model, and you have cell phone A, someone else has cell phone B, and your memory is twice as much as that person's memory. I want to train a parent model in the cloud. I give it to you. I cut the model down to the size that your cell phone will be able to hold. I cut it down to a different size for them. I don't need to revisit the data. I don't need to do refinement. I don't need to do anything. What do I lose? What I lose is, between 10 and 20 and 30 on this plot, or the difference between 10 and 20 and 30 in this plot. Meaning, I don't lose anything. So you can do that, and so that's something else we're looking for at. You can also apply this to a range of other sort of PDE and dynamical systems type problems where you would expect this continuous dynamics to exist. So with that, let me wrap up. And so there's a range of things we're doing here. I think the high level theme is you can have very non-trivial coupling of ideas from dynamical systems and continuous theory with ideas from discrete machine learning and traditional approaches to machine learning. And we're looking at those. And ContinuousNet does it, I think, in a particularly elegant way. And so with that, let me wrap up. And if there's any questions, I can be glad to answer those or tell you sort of other things looking forward that are related that we're looking about that I didn't have a chance to go into enough detail, but that are related to the details of ContinuousNet.
So Michael, thank you for a great talk. There are a couple questions that came up during your talk, and we'll just ask those in the few remaining minutes. The first comes from Steve Taylor from NJIT, who is curious to what extent you have investigated the application of physics-informed autoencoders to other physics, for instance, non-fluid equations, such as Maxwell equations, Lagrangian Hamiltonian-derived equations, or otherwise. For example, are there certain classes of dynamical systems, say a constrained class of differential operators that define them, for which your techniques will always approximate the analogous continuous dynamical system well?
Yeah, I mean, good question. There's a list of things to do, and that's on our list. We haven't looked at, other people have looked at things like that. We haven't looked at that in a lot of detail. The improvement that I alluded to here was something where essentially we applied this to ideas in Koopman theory for operators that were invertible. You enforce sort of a consistency both forward in time and backward in time. And so we got improved results there. We have evaluated, I think in the paper was only the fluid flow, but we've evaluated in other classes, but not fully at the level of the question. And that's something else we're sort of looking at, but not in as much detail as we'd like yet.
Thanks. There's also a few questions from Pantelis Monogiotis at NJIT. For control applications, domain can, however, be modeled by, for instance, via an VAE plus RNN and a controller that can be trained to maximize expected reward. Do you have any thoughts on the application of continuous nets in control apps such as robotics, where a policy needs to be learned from, for instance, raw pixels?
Yeah, I've wondered about this. I don't have a good sense of how those sort of feedback mechanisms map to the leading order sort of axis of variation that I was trying to describe. The leading order is, computer science, and there's data in front of you, you chew on it and you get a model. And it's, in a lot of things where you have something under the hood, you could do it in statistics or you could do it in science. The model doesn't matter. How the model performs tomorrow or on different data matters. And so that's a robustness or stability. A lot of people now in ML and neural networks and CS, have applications like the one just described, where really you're doing some sort of exploration. My sense is that when they do that, they develop a broadly parameterized class of models to explore, and the success of the model is loosely along the lines of the sufficient condition type theory you'd get guiding traditional sort of ML theory, not of the form that you'd get in scientific computing with this extrapolation. And then it's validated when you see a few success stories, but there's a big enough theory practice gap that you haven't really closed it in that way. So that's my sense, but I don't know enough to stand by that if someone really wanted to argue with it. But that's my sense, that it's pretty different in that sense.
Thanks. And Pantelis had a second question about the fact that we're moving into continual learning where catastrophic forgetting must be addressed. Is it possible to have this continuous learning physical systems?
Continuous learning physical systems. Like, okay, so let me just clarify maybe the question. So for example, in a very similar way as we have continual learning on trying to when we learn, let's say, a task, when we go to find another task in our path, let's say we are, let's say, a robot going into an environment, we are seeing a bunch of objects, we're learning some things about some classes of objects, and then we can potentially learn others that are coming, following those in some kind of trajectory without necessarily forgetting the ones that we learned before. In a kind of a similar setting, can we learn sort of physical sort of autoencoders, physical driven kind of autoencoders without really forgetting? Let's say, for example, I have some autoencoder that captures the model of hitting with a racket a tennis ball, but then when the ball becomes a foam ball, then I should really always learn that, how to achieve the goal, let's say, in that kind of game, without necessarily forgetting how to hit the tennis ball as well. So I guess that was the...
Yeah, I don't know. I don't know what continue. My sense is that the pain point there is not the continuity of ContinuousNet. ContinuousNet is continuous, but there's a couple types of continuous things. And one, to oversimplify, right? I mean, one is when you remember, there's a time scale and you remember 2 days back and you forget everything else. And so a different one is when you can really remember stuff sort of from long ago. And a lot of algorithms, a lot of methods, a lot of regularizers, cook in a time step, even if you don't intend to. And the limit people go to get Gaussian processes when they, I don't mean Gaussian Gaussian fluctuations or something when you have a stochastic differential equation or something, cooks in a time step like that, and that often sort of wipes out what you learned before a certain time step ago. I mean, I think there's a challenge in how to incorporate You see it in financial systems, you see it in actually, real neurons, not neural network. I mean, real, how do you incorporate, heavy tails, some sort of long tail time series back in time? And my guess is that you'd have to learn a model where you don't learn a fixed number of things, not a low rank space, not something, and then you cut off, which is what a lot of models do when they have sort of a cutoff. And we thought about that in the context of the Koopman improvement to the stuff I was talking about in the first half, because again, my sense, and someone could disagree with this if they knew the area much finer, but my sense is that the following is true. Either one of the reasons Koopman is popular and or the 99% use case where it's used is when you have essentially a certain time scale. You want to memorize, you want to learn stuff, 2 days back. And so then you turn the discrete thing into, so you turn the nonlinear dynamics into a linear dynamics, but you're really only doing that because you're learning it 2 days back. That methodology doesn't play well with this heavy tail thing where you need to remember very far back. Because what you're saying is not the taxonomy is not that I have an infinity of things and I just remember them. The taxonomy is there's a ball and the ball has a certain weight. And if I'm going to throw it, it's going to behave one way, but if its weight is very different, it's still going to move through the air, but it might have a different friction or something. So there's sort of a hierarchy of what you've learned. And for that, you need something about these heavy tail dynamics. And I don't think that meshes well with either of these approaches, probably.
Okay, thank you.
So Michael, thank you again for giving this lecture. It was very in-depth, and I really enjoyed hearing the current work that you're up to. Hopefully we get to see each other face to face in the future.
Hope so. Hopefully sooner rather than later. Yeah.
So thank you again.
All right. Take care.